All right, so now that we know what's going on inside the sun, let's talk about the layers of the sun. Now, I recommend that you print out that sun worksheet that's in our week's activities. On that worksheet, you'll see that there's a diagram where you can label the layers of the sun, talk about what's happening in each layer, and the temperature of each layer. Okay, we're going to be going through those layers in this lecture, so you might want to get that out and write in it as you go, right? However it works for you, right? You can do it afterwards or you can do it during the lecture. But have that in mind. You want to collect information on the different layers, what order they go in, what their temperatures are, and what's happening in each of those layers. So let's talk about the sun's layers. Our first layer, after the core, of course, right? We know what's happening in the core, right? That was our last video, all those fusion reactions happening in there. After those fusion reactions, though, that energy that's created in there, those gamma rays, need to get out, right? That energy needs to get out to us, right? We know the sun heats us, so somehow that energy from the sun is getting from that core region out to us. Our first step in getting that energy out is for those gamma rays to bounce around inside what we call the radiative zone of our sun. Those are actual photons created in those fusion reactions. Those photons are going to bounce around through the material that's in the sun. Now, this material that's in the radiative zone is dense, right? That material is packed pretty tightly together, right? It's still got other layers above it, so that material is going to be pretty tightly packed. This means that the photons don't just go directly out. What they're going to do instead is they're going to bounce around, kind of like that. There they go, bouncing around, right? Working their way out. You notice that sometimes those gamma rays are going backwards, sometimes they're going forwards, right? They're bouncing around off of all of those little dots that are in there. This means it takes them a long time to get out, okay? All of that material there is working like little linebackers to keep those gamma rays from getting out, okay? This is energy transport via radiation, right? Radiation is another word for light energy, like these gamma rays that we have. So this is our radiative energy transport, just getting those gamma rays out to the end of that radiative zone. Once they get to the end of that radiative zone and hit the convective zone, those gamma rays are absorbed into the gas that's out there. They're going to heat that gas up, right? The gamma rays themselves, their energy is taken in by this gas. Now the gas is going to move through what we call bulk motion. Okay, this bulk motion means that we're going to have material rising up and falling in a convective pattern. Okay, convection happens when hot, less dense material rises up and cooler, denser material sinks back down. It's a continual cycle of hot, less dense rising, cool, more dense sinking. Convection doesn't just happen inside of our sun. It happens really everywhere here on Earth. All of our Earth weather patterns are dominated by this convection. Convection happens in the mantle of our Earth. Convection happens in a pot of boiling water, right? Convection happens inside your house, right? If you live in a 2-story house, you probably have noticed how the upstairs is always hotter. That's because that hot air rises, right? The cool air sinks back down. That's convection, right? Making your house hot on the top and cool on the bottom. Okay, so the same process is working inside of our sun. Hotter gas rises back up, cooler gas sinks back down. The temperature in the convection zone has dropped yet again. We were at about 7 million on average in the radiative zone, now about 2 million on average out there in the convective zone. How do we know this process is happening of convection? We can see the result of it. Okay, so remember, things that are hotter are going to glow more brightly. Things that are cooler are going to glow less brightly. So if we look at this picture, those darker areas are going to be areas where the material is cooler, where that material is sinking back down into the sun to be reheated. The areas that are white or really light yellow, those are going to be the areas where that hot material has just risen back up, right? This pattern we call granulation. This pattern changes. Okay? It's like that pot of boiling water where that pattern is constantly changing, right? This is just a snapshot of that pattern. Okay, but this pattern will be constantly changing. right? Like a big pot of boiling water. Let's try a question. That brighter area means it's got to be hotter, right? That's where that hotter material is rising up, right, to make that area brighter. Just above the convection zone, or the convective zone, some books call it one or the other, we have what we call the photosphere of our sun. The photosphere of our sun is the visible surface layer of our sun. This is the part that we see. Okay, now you shouldn't go out and look at the photosphere of the sun, right? Looking at the sun is bad for you, but if you happen to just notice it, right, take a photograph of it, you're taking a photograph of the photosphere of the sun. Okay, that's what you see with your eyes. Now the photosphere is a really thin layer. Okay? It's about 500 kilometers thick, which sounds like a lot, right? 500 is a lot. But compared to the overall size of the sun, really not much at all. Okay? Down in this bottom picture here, you'll see that very thin white stripe there between the yellow and the pink. That's the photosphere. That's how thin it is. Okay? And they've got the Earth down there for scale, right? Very, very thin layer there. The photosphere is kind of like the skin of the sun, right? It's the division between the interior of our sun, right? The radiation zone, the convection zone, the core of our sun, and the outer layers of what we call the solar atmosphere out there. The photosphere is the part that's about 6,000 degrees, right? 5,800 degrees. And the photosphere is actually the coolest part of our sun there. Okay. You can't see through the photosphere. Okay, it's highly opaque, right? You can't see through it. The photosphere, though, is the part that's going to produce all of the energy that we see, right? All of the light that we see, the heat we feel, that's all from the photosphere. Okay, what the photosphere does is it's going to take that energy that's come up through convection, it's going to absorb that energy, and then it's going to re-radiate, and it's going to radiate a nice black body spectrum back out. Okay, so the photosphere itself is going to make this nice continuous spectrum of light, right? Full rainbow, right? A nice black body spectrum from the energy that it's getting from the layers underneath. Okay, so those gamma ray photons don't make it out of the sun. Those gamma rays that happen from the fusion reactions, they're going to work their way out through the radiative zone. They're going to get absorbed in the convection zone, and then their energy is going to get absorbed again by the photosphere. Then the photosphere is going to re-emit a whole new batch of photons, right? Visible light, infrared, ultraviolet, all that good stuff that's going to come out our way. Okay, so all of the light we see is from that photosphere itself. Above the photosphere, we have the areas of the solar atmosphere. The first area of the solar atmosphere is the chromosphere, and you're seeing that as these pink spikes here on the bottom. Those pink spikes are their representation of the chromosphere. Outside of the chromosphere, you then have the solar corona. Okay, so we've got to look at those two a little bit. Hopefully you got this, right? All that visible light is, of course, from the photosphere, right? That's where it's coming from. So, I said that we can't see through the photosphere, right? I've told you a lot about what's going on inside of the sun, though, right? I've told you that there's these reactions in the core, right? We know about those from the neutrinos. Then I told you there's this radiative zone and the convective zone, but then I just told you that you can't see through there, so how would I know? We know the layers of the sun based on helioseismology. So helioseismology works much like seismology the Earth does, right? We live in earthquake country, right? So you guys know what seismology is here on Earth, right? Seismology is the study of those earthquake waves, right? The waves of the earthquake then go through the body of the Earth. If we watch how those waves go through the Earth, right, with all of our seismographs, we can figure out what's going on inside of our Earth. Same thing is true for our sun. Okay, if we look at how these waves move through the body of our sun, we can figure out what's going on inside of our sun. Okay, We're going to do this with Doppler shifts, right? Astronomers do almost everything with Doppler shifts, it feels like. Okay, so if you notice the wave pattern up here with this green line, right? You see it's going up here in the blue part. And then there's kind of a down part here where it's red, and then up again in blue, and then down in red. Okay, that's what they're trying to show you here, right? So imagine this bottom ball as like a spiky ball. Okay, the blue parts are coming out towards you, and the red parts are going into the ball, right? So the blue parts are the spikes. Okay, that's what this wave pattern looks like, right? Because we're going to get a blue shift when something's coming towards us. We get a red shift when it's going away from us. That's what they're trying to indicate here, is this kind of wave pattern there. This wave pattern, obviously, this is a computer model of the wave pattern. The real wave pattern would be much more complicated than that. But this is how they're going to figure out what's going on inside of our sun. So let's talk about that layer of the solar atmosphere just above the photosphere. That's our chromosphere. Okay, chromo, you might recognize that word as the root word for color. Okay, the chromosphere is called the chromosphere because it comes up pink. Okay, when we look at it, we're usually seeing this nice pink color in the chromosphere. Okay, the chromosphere, oddly enough, actually gets hotter. Okay, so a little different than Earth's atmosphere, right? Usually if you're going up through Earth's atmosphere, it gets colder as you go up. Not the same on the sun. There's some magnetic effects that trap the heat there. So actually, as you get further away from the sun, it actually gets a little bit hotter. And then it gets a whole lot hotter. Okay, so throughout the chromosphere, it's getting hotter. Then it hits this part called the transition region, where this temperature jumps up to about 1,000,000 degrees. Okay, so much hotter up through the chromosphere. The chromosphere does have structures in it. Okay, and you can see those. There's kind of a side view down here. If you can see that faint circle right here, that's the size of our planet Earth. Okay, you can see these structures in the chromosphere are about as big as our Earth is. Okay, these are gigantic structures. These structures are something called spicules. Okay, here they are here. Okay. These spicules are filaments of gas that are coming up from the photosphere and rising up through that chromosphere. Okay, like little hairs almost. We can see them as pink because they're emitting in that H-alpha emission line spectrum. Okay, so if we look at just the gas itself, we can see that nice H-alpha emission line. It's hot gas that's coming up through there. Each one of these little filaments is going to last for about 5 to 15 minutes, right? Not very long at all, right? They come and go. These little filaments, though, they're well, I call them little. They're little compared to the sun, right? But they're big compared to our planet Earth. Above our chromosphere, we have the solar corona. Okay, so usually seen in pictures kind of like this one down here. Okay. And in that bottom blue picture, they've got something that's blocking out the sun's surface itself, okay, so that you can see that corona around there, right? This thing in the center here, right, a coronagraph or an occulter, it's blocking out the sun, right? The sun is behind that, so that you can see that stellar corona, right, all the way out there, okay? There's some activity on our sun, depending on what cycle our sun is in. So sometimes on our photosphere, you'll see these dark spots. Those are sunspots. If we look in the chromosphere, we'll also see there's a little bit of activity happening wherever the photosphere has a sunspot. We're going to see activity happening in the chromosphere just above that. Okay, and that'll often correlate with what's going on as well in the corona down there. The corona gives rise to what we call the solar wind, okay, actual material that's streaming away from the sun. Okay, there's a little coronal hole there, right, which I think is funny because it's star-shaped, right? There's a little nice star-shaped coronal hole there. That coronal hole is one of the origins of that solar wind coming off of our star. The solar wind is a constant stream of actual material that's coming off of the sun. Okay, so not just light, but actual stuff that has mass, right? Particles, charged particles that are coming off of our sun. This means that the sun is constantly losing an amount of mass, about 1,000,000 tons every year, which is a lot of stuff. That sounds like a lot of stuff, doesn't it, right? That's a lot. But if you compare it to the entire mass of the sun, remember it's 333,000 times the mass of the Earth, it's not that much. Okay, it sounds like a lot, but compared to the overall mass, it's not that bad. This solar wind is going to be what creates the aurora borealis that we see in our northern lights.